In this video, we're going to talk about finding composite functions. So first we're going to go into some background of why we're finding composite functions, then we'll talk about what a composite function is, and we'll go about evaluating two ways algebraically, using tables, using graphs, and then we'll talk about finding the domain of composite function. So why are we finding composite functions? Let's say we have a bakery that makes cookies. We're given two equations. One, S of C, gives the amount of sugar needed per cookie. Another equation, P of S, gives the price per gram of sugar. What if the baker needs to know how much money is spent on sugar for each cookie? We'll want to use composite functions. So what are composite functions? In that example, we were given a number of cookies where we could plug it into S of C and get the amount of sugar, and then we could plug that into P of S to get the price. Using composite functions, we can go straight from number of cookies to price. And this is denoted as f composed g of x, or f of g of x. When we're evaluating, let's say we're given f of x equals x squared plus 3, and g of x equals the square root of x plus 1, and we need to find f of g of 3. So for the first method, we can just plug in 3 to the inner function, g of x, and we'll get that g of 3 equals the square root of 3 plus 1, which equals the square root of 4, which equals 2. Then we'll take the output of the inner function and plug it into the outer function, f of x, to get f of 2 equals 2 squared plus 3, which equals 4 plus 3, which equals 7. So we know that f of g of 3 equals 7. In the second method, we can first find the composite function by plugging in the inner function to the outer function. So we'll plug in g of x as the input, like so. So f of g of x, f composed g of x, equals the square root of x plus 1, quantity squared, plus 3. And then we'll evaluate to get x plus 1 plus 3, which equals x plus 4. So x plus 4 is the composite function. Then we'll plug the x value we're given, which is 3, into the composite function. We'll get f composed g of 3 equals 3 plus 4, which equals 7. So again, we get f of g of 3 equals 7. And then if we're evaluating with a table, we'll first want to look along the x-axis and find the x value we're evaluating at. So we're evaluating at 3. We'll want to go to the inner function first and find the output there. So that equals 2. The output for our inner function becomes the input for the outer function. So we'll look at 2 for the x value, and then bring it along to f of x, which is the outer function. And again, we'll get f of g of 3 equals 7. And then when we're looking at a graph, here we have the graphs of f of x and g of x. Again, we'll want to find x equals 3 along the x-axis, and find the y value for g of x. Here we get 2, and then we'll use that y value, and again look at the x-axis and try to find the y value for f of x, so we'll bring it along and find that again it equals 7. Now when we're finding the domain, if we're given f of x equals negative 2 over x, and g of x equals the square root of 1 minus 3x, if we're finding the domain of the composite function f composed g of x, first we'll find the domain of g of x. So here the g of x is under a radical, so we know that the inside has to be greater than or equal to 0. So if we set 1 minus 3x is greater than or equal to 0, and then we solve for x, subtract 1, get negative 3x greater than or equal to negative 1, divide by negative 3, and we get x is less than or equal to 1/3. And then we'll find the domain of f of x. Here we're dividing by x, and we know that you can't divide by 0, so the only number excluded from the domain of f of x is 0. Then we'll want to exclude the outputs from the domain of g that aren't in the domain of f. So we know that the only number excluded from the domain of f is 0, so we'll want to find when g of x equals 0. So we set the square root of 1 minus 3x equal to 0, and then we'll want to solve. So 1 minus 3x equals 0, subtract 1, divide by negative 3, and we'll get x equals 1/3. And then we know that x also can't be 1/3, and we'll take that and look at the domain of g of x again, and we'll find that the domain is negative infinity to 1/3. In this second example, we have 2 square roots, so it's a little different. Again, we'll want to find the domain of g first. So we'll get, again, it's a radical, so it has to be greater than or equal to 0. So 4 minus x is greater than or equal to 0. We'll solve for x, subtracting 4, divide by the negative, and we'll get x is less than or equal to 4. And then we'll want to find the domain of the composite function. So first we'll want to find the composite function, plugging in g of x for x in the equation of f of x. So we get the square root of 4 minus x plus 1, and then we'll find the domain. So it's all under a radical, which means that it has to be greater than or equal to 0. So the square root of 4 minus x plus 1 is greater than or equal to 0. And then subtract 1 on both sides, but we know that 4 minus x can actually only be greater than or equal to 0, so we can change that, and then solve for x again. 4 minus x greater than or equal to 0, which we solved previously, so we know that x is less than or equal to 4, or the domain is negative infinity to 4. So let's review what we talked about. We know that composite functions are two functions connected through an input and output. One input is plugged in to get the output, just plugged in again to get the new output, but we just have a simpler equation for that. And we can evaluate them using original functions, or with a composite function, or using a table, or with a graph. And we can find the domain by finding the domain of the inner function first, and then we can exclude the x values that result in outputs that aren't in the domain of the outer function. And here are the sources for this PowerPoint.